Uh-oh. There we go. Looking specifically at the calendar, it's kind of a quick turnaround for the first unit. That's good news and bad news, right? Because there's not a whole lot of stuff, but it's probably hard stuff if that's the only stuff that's on the test. This week is usually not hard. This antiderivatives day is probably the trickiest day of the group, but then we have a full day to review, an extra half a day to catch up, go over things, and take the test. So I think this week is okay. That Monday is the tricky day of the unit, but you'll be fine after that. All right, well, let's talk about Riemann sums. Actually, let's talk big picture for a second, because all of this stuff in this first unit goes together. I mean, I guess that's always the case, or it should always be the case for a unit in any class, but it's really tied together more than most, and it's tricky to figure out what's the best order to present it in, because you kind of need to know it all to see how it fits together. And that's why the units are like way out of whack here. We're going to do 4.2, and then 4.6, and then 4.3, and then 4.1. It doesn't matter which order you go. You kind of have to get them all before you see how they fit together. And that's why we have the 2 review days in to kind of back up and say, okay, now I see how it all fits and understand why it doesn't really matter what order you go in. You got to get them all before you can put them together. And so that'll probably make more sense after we've seen all these lessons. But let's talk about Riemann sums. And again, since you don't have all the other lessons, it's going to be a little bit like, where did this come from? Why are we doing Riemann sums? What is the point? And for now, it's kind of just a trust me, it'll make more sense later. But it wouldn't matter where we started, I'd have to say that. Trust me for now, we got to get the whole picture before it makes sense of all of it. The fancy word for that is irreducible complexity. If you pull out one strand and the whole thing kind of falls down. It's a little bit of Jenga. We got to build the whole tower, but you can't build the whole tower in one day. But small picture, what we do today is really not that difficult. So how it attaches to calculus is maybe tricky, and we won't really understand today. But just the details of what we're going to do today is not that bad. All right, Riemann sum. So some dude named Riemann long ago decided that he could use rectangles to approximate area. Specifically the area under a curve. So you get some weird curve, you want to know how much area is underneath it. Well, it's probably not some standard geometric shape. So Riemann figured out, or suggested, that we could just estimate it. We'll just put some rectangles in there and it'll be close enough for what we want to do. So there's really not a lot of theory behind this. We can jump right in because the theory behind it is the area of a rectangle is length times width. Like that's the underlying math theory for today. Maybe we should have done a warm-up with 14 area problems. Length times width, length times width, length times width. Because in some ways, that's really all we're going to do today. In fact, it may be worth it to emphasize that. Like, don't get lost in the details today. All we're going to do today is add up a bunch of rectangles. That's all we're going to do. You're thinking, well, it's going to get more complicated than that, right? Like, yeah, yes. But at the end of the day, all you're going to do to approximate area is add up rectangles. Length times width, plus length times width, plus length times width. That's it. All right, find the estimate. So it won't be exact, it'll be an estimate. An estimate of the area using rectangles. There are other methods, but we'll save those for later. So today is rectangles. Find an estimate of the area the region bounded by, so marked off by, fenced in by, corralled by, f of x equals x squared and the x-axis between x equals 0 and x equals 2. So we're going to draw a picture of that to figure out, exactly what we're estimating. There's more to the problem statement, so don't draw your picture right here. I'm going to finish the problem statement, but I want to pause right here to draw what we know, to just understand what they're trying, see if we can understand what they're trying to ask us to find. So x squared between 0 and 2, so that's just a parabola. And the bigger you can make your picture, probably the easier it'll be, but this is big enough, what I've got. Y scale's a little off there, but that's okay. So parabola goes through 0, 0, and 1, 1, and 2, 4. And we know, roughly what it looks like. Something like that. So I don't want to shade it because we're going to shade some other stuff. I guess I could shade it super lightly and I'll use a different color later. So I don't know if you want to shade this or not because we're going to put lots of stuff on this picture. But that's the area we want to find, or really want to estimate, because I don't know how to find that. That's a weird shape. I mean, kind of like a triangle, but it's not a triangle. We're going to estimate it with rectangles. And more specifically, so here comes the rest of the problem statement, right? Like, well, how many rectangles should we use and where should we draw them? Using a right Riemann sum and 4 subintervals. And you don't really even need the word sub. I don't know why they use it, because this really just means 4 intervals. So 4 rectangles. So 4 rectangles. Riemann sum means rectangles. And right means from the right. So we're gonna divide it up into 4 rectangles, or 4 segments, and then we'll draw the rectangles from the right. So this one's convenient because it's only 2 wide and we want 4 rectangles. So I guess let's show the process, even though it's an easy one. So the width of each rectangle is going to be the total width divided by however many rectangles there are. So the total width is 2. We want 4 rectangles. So each rectangle is going to be 1/2 wide. Probably didn't even need to show that for that one because it was simple enough. Most of you would have figured out, well, if we want to fit 4 rectangles in a space of 2, they need to be 1/2 wide. So I'm going to divide up my divide up my graph into four sections, four intervals, four subintervals, however you want to phrase that. And because it says right Riemann sum, we want to come from the right edge of each interval. So a left Riemann sum would mean, well, it's come from the left. Right Riemann means we'll come from the right. So from the right of each interval is where we'll draw our rectangles. And so we're going to estimate our area using these four rectangles. A little side note, is that going to be an overestimate or an underestimate? Over, because all those rectangles are bigger than the actual area. So it's going to be an overestimate. But sometimes it's good to know that. Like whatever area I get, I know it's a little bit more than, or maybe a lot more than, the actual area. Now, this is one of those things where if you look in a textbook, they give you all sorts of crazy formulas, and it's hard to follow out. Where did all that stuff come from? All they're doing is adding up rectangles. So we're just going to say the area is approximated by, right? So little squiggly lines, because we're going to estimate using the area of the four rectangles. So you can label all sorts of stuff with A's and B's and divide by N, and don't worry about that. If you look in the book, it gets confusing. I want you to think Riemann sum means add up rectangles. Everybody can add up rectangles. That's all we're going to do is add up the rectangles. So the first rectangle is 1/2 wide by something high. That height is the tricky part. It's a y value, so it's the function evaluated at 1/2. That's the first rectangle. The second rectangle, still 1/2 wide. I don't have all my colors up here. See if this works. Whoop, that's a little bit bold there. That's a little bit much, but you get the idea. F of 1. So the height of the second rectangle will be f of 1. Third rectangle is 1/2 wide. F at, what's that x value of the third rectangle? 3/2 or 1.5, either way you want to say that. And then our last rectangle, 1/2 times f of 2. At this point, you should always check and make sure that you have the right number of rectangles, because it's easy to get an extra rectangle in there, because you think, well, maybe I should have done f of 0 and f of 1/2 and do like each height, but then you'd have 5 rectangles. So 1, 2, 3, 4 rectangles. I'm just going to add them up. So 1/2, f of 1/2 is 1/2 squared. F of 1 is 1. F of 3/2 is 3/2 squared, or 1.5 squared. I don't know how you would want to write that. And f of 2, that's an easy one. 4. So let's see. The book is almost always going to factor out the 1/2. If you're doing a calculator, it doesn't matter either way. But I can pull that 1/2 out front from all of them. Be careful, because usually our rectangles have all the same width, and so you can do that. Occasionally we'll throw you some rectangles that aren't the same width, and so you wouldn't be able to factor it out. You just have to add up whatever the weird rectangles are. So be careful, you can't always factor that out. So 1/4 plus 1 plus 1.5 squared is, oh yeah, safe stop, is 1.5 squared. In fact, we could leave that as our answer right there. That looks a little bit unfinished, but it also has an advantage of it's clear to see where it came from. So you could leave that as your answer. If you typed it all in the calculator or did a little bit more work by hand, you'd get 3.75. But I do want to say that that is a safe stop, that last step. And you already told me this, that that's an overestimate. Now, the book, I think, expects you to memorize what I'm going to write next, but I don't want you to memorize this. I want you to be able to look at a picture and figure it out. For an increasing function, which is what we had, for an increasing function, a right sum overestimates. But that's not something you need to memorize. That's something you can sketch out and figure out. If you're increasing, then if you're taking the right-hand sum, you're always taking a higher value, and so your rectangles are always above or outside your area, so it's going to be an overestimate. So I don't know what the actual area is, but I know it's less than 3.75. And so Riemann came up with this plan to figure out a way to estimate areas. Let's do a left Riemann sum. Of the same area. So I'm going to sketch it again and draw it again. So same parabola. Four subintervals. So we're still doing area between x squared and x-axis between 0 and 2. But now we want to approximate that with left rectangles. So I'm going to draw my rectangles from the left. It gets a little bit tricky, especially for that first rectangle. Because how tall is the first rectangle if I'm moving from the left over here? How tall is that first rectangle? 0. So I guess you could say there's not a rectangle, but it'd be maybe clearer to say it's a 0 height rectangle. So I'm coming from the left. This is going to be an underestimate for sure, because all my rectangles are underneath the curve. So 1/2 times f of 0. So this time I'm starting at the left. The last time I started at 1/2 because I had to start at the right. Now I'm starting on the left. So f of 1/2, or excuse me, f of 0, f of 1/2, f of 1, and f of 1.5. But not f of 2. Right? I don't ever use this f of 2 point because that would be That would be a right-hand rectangle. I'm always coming from the left, so I don't ever get to that far right point. We already said that this first rectangle is a 0 rectangle, so you can throw it out if you want, but just to remind myself that there's 4 rectangles there, I'm going to leave it there. And actually that would be a safe stop, whatever that is. Again, you can obviously throw out the 0, but I think it's probably helpful to leave it there, because now it's clear that you've added 4 rectangles. 1, 2, 3, 4. If you add them all up, we get 1.75. Which we already said is an underestimate. Say for an increasing function, a left sum underestimates. Now we could ask all sorts of questions. We could say, well, what about a decreasing function and a right-hand sum, or a decreasing function and a left-hand sum? And you can memorize all 4 of the combinations, but I don't memorize those. You just sketch them out and draw some rectangles, and you quickly realize, oh, they're all underneath, or they're all outside, and so you can figure out if it's an underestimate or an overestimate. By the way, there's another name for an underestimate. That's called a lower sum. So that kind of fits with under and lower. Those go together. And for an overestimate, we could call that an upper sum. Take a minute to literally zoom out on this problem. I can say for sure that the area underneath that curve, I can't say for sure what it is, but I can say for sure that it's more than 1.75 and less than 3.75. Because 3.75 was an upper sum, 1.75 was a lower sum. So I've at least got bounds on what that area is. Sometimes, it depends on how we ask the question, we can ask for a right sum or a left sum, but we can also ask for an upper sum or a lower sum. So if we ask for upper or lower, you've got to look carefully and figure out, well, which side do I need to come from to make sure it's above or below. A few more examples to go. But what could we do? Just kind of peeking ahead here. What could we do to get a better, Macy?
I just have a question. So why would you start at 0 for the left and point out at 0? Is it because it's not?
Because if I zoomed in really far here, so just by looking from 0 to 1/2. Like the height at that first, I got to come from the left if it's a left sum.
Mm-hmm.
So coming from the left means using this height. So the height of that first rectangle is 0. So it's not really a rectangle, but that's why I picked this problem, because it's kind of confusing. Does that answer your question?
Yes.
Okay. So how could I get a better estimate of that area? Like 3.75, 1.75, I guess that narrows it down a little bit. But how could I get a better estimate of that area? There's a couple different answers. More rectangles, right? If I threw 1,000 rectangles in there, well, it'd be a pain to add them all up, but I'd have a really accurate answer. Any other suggestions?
If you found like an area of like a triangle on top of the rectangle.
Okay, that's exactly what we're going to do tomorrow. She said if we found the area of if we stuck a triangle on top of the rectangle, right? I mean, that's thinking outside the box a little bit, but that would definitely get us a better approximation. If we stuck a triangle on top of that rectangle, what would the entire shape be? Geometry experts. If I stuck a triangle on top of that rectangle, it'd be a trapezoid. Right? So if I put a triangle on top of that rectangle, I'd have a trapezoid. That's tomorrow's lesson. Tomorrow we'll do the trapezoid rule. But that's not for today. Today we're just adding rectangles. So 2 ways to be more accurate: do more rectangles. That's doable. It's just kind of a pain to stick 8 rectangles or 10 or 20. But a little bit easier way would be trapezoids. We'll do that tomorrow. All right, example, I guess it's example 2 because that first example was all one example. Example 2, find the upper sum. So it's not telling me right or left. We'll have to figure out if we want to use right or left to get us an outside, upper bound, upper estimate, upper sum, over estimate. For the area under f of x equals 9 minus x squared. On 1 to 3 with 4 subintervals. Okay, well, let's draw the picture, figure out what area we're trying to approximate, and then we'll worry about upper, lower, right, left, intervals, width, all that stuff. So let's just get a picture of 9 minus x squared. Especially from 1 to 3, but I'm probably going to start at 0 because 9 minus x squared, that'd be a upside down parabola that starts at 9. Or I could just plug in points. If I plug in 0, I get 9. If I plug in 1, I get 8. If I plug in 2, 9 minus 2 is 5. If I plug in 3, I'm down at 0. But I only want 1 to 3, so from 1 to 3, and I want to upper sum. Actually, let's do 4 subintervals first. So the width of each interval, the total width is 2. We're going from 1 to 3. We want 4 subintervals. So each one's a half. So my rectangles will be 1/2 wide. So there's my 4 intervals. I want an upper sum though. So if I want an outside sum, if I want to overestimate, which way do I want to draw rectangles? Get my position right. Do I want to draw them coming from the left, or do I want to draw them coming from the right? From the left or from the right? Of course, if I put them on the page like that, from the left, that'll give me an upper sum. So my area approximately equals. Some people are going to think ahead and they're going to factor out the 1/2 right from the get-go. I'm not ready to do that yet. I'm going to write the 4 rectangles. If you get confused, you're just adding rectangles. So 1/2 times I guess it's 8, but I'm going to write it as f of 1 to start with. Plus 1/2 f of 1.5 plus 1/2 f of 2. 1/2 f of 2.5. Here's the trouble you get in the pattern. So do I need to write 1/2 f of 3? No, that would be a fifth rectangle. That would be going over one more, or a right hand. So I've got my 4 rectangles. Let's see. So now I'm going to factor out the 1/2. I'm comfortable now that I've got 4 rectangles there. F of 1 we already know is 8. F of 1.5. How about we just do this? All right, we're going to the calculator, or we're leaving it a safe stop, so I don't need to get into the details here. That's f of 1.5. F of 2. 9 minus 2 is 5. F of 2.5, I don't know, it's 9 minus 2.5 squared. And that is a safe stop. Like, that is perfectly okay to leave it like that. I mean, arguably it's better to leave it like that because you can see where all the pieces are. In fact, to illustrate it's okay, we'll stop there. We don't even want to get an answer. We'll say that that's it. If it's bugging you, it's 11.25. But we're okay to leave it like that. All right, let's do one more. Find a right hand sum. Sometimes we say hand, sometimes we just say right, sometimes we say Riemann, sometimes we don't. This all kind of means the same thing. A right hand sum, a right Riemann sum, that all means the same stuff. For area under f of x equals 1 over x on 2 to 6 with n equals 4. So we didn't specify, we specified 4 subintervals, but we've stopped saying subintervals. We just say n equals 4, and you know that means 4 rectangles, or 4 subintervals. I guess if you did enough of these, you wouldn't have to draw the picture. You could kind of just know, if I'm coming from the right, what that means. I'm going to draw the picture on these. 1 over x. Okay, I know what that looks like. All right, something like that. But I need to be a little more specific here. 1, 2, 3, 4, 5, 6. Oh, this is going to be... I'm going to make my scale a little wacky here because I'm peeking ahead. If I plug in 1, I get 1. If I plug in 2, I get 1/2. If I plug in 3, I get a third, a fourth, a fifth, a sixth. Right hand sum. Well, actually, let's block off 2 to 6 because that's where we're looking. I really didn't need to draw the rest of it, but to kind of get the full picture. N equals 4. So how wide are my rectangles going to be? 1. This is kind of a nice one. Total width is 4 subintervals. So we want 4 rectangles, and they'll each be 1 wide. Right hand sum, so I'm coming from the right. So I would even start with the rightmost rectangle if I'm going to come from the right. So that one, that one, that one, that one. It's going to be an overestimate or an underestimate? Under, right? All my rectangles are under, so. again, if you want to factor out the 1, you can, because the 1's the same width for all of them. I don't like to do that, again, because you're not always, we're going to give you some that the widths aren't always the same, so you're not able to factor it out. So if you get in the habit of factoring out, and then we hit a set of rectangles where they're not the same, you got one small one and one wide one, you're going to feel like you're stuck. But you're just adding rectangles. So 1 times, what am I doing here? F of 3 plus 1 times f of 4, 1 times f of 5, and 1 times f of 6. And obviously it's 1, so I don't need the 1 at all, except that I want to kind of preserve this idea that I'm adding rectangles, so I'm going to leave it in there. So 1 times 1/3, 1 times a 4th, 1 times a 5th, 1 times a 6th. Safe stop, we're good. If you really want an answer, you just put it in the calculator, and you get 0.95. You already said that that's a lower sum or an underestimate, just based on your picture. Again, the over and under stuff, to me, it's too tricky to memorize. Okay, increasing and right would be over. I don't have it memorized. I just think about it. So when it asks for those, just draw a picture and see what you get. All right, the assignments from the book, page 263. 25, 27, 29, 33, and 35. Again, it's just a geometry lesson today. You're just adding up rectangles is all you're doing. And why that matters to calculus, we'll put it together a little more later. All right, I'll take a picture of that and I'll post it in Schoology. And obviously answers are in the back of the book, or Calc Chat. Don't forget about Calc Chat. Oh, you need to know the section number, and it's 4.2. So if you're Calc Chatting for answers, which is encouraged, it's not cheating if you're using it correctly anyway.